Hello, my name is Ivan Božić and I'm a PhD student in the Translational Biophotonics Laboratory at Tulane University. I will present to you our work on quantitative assessment of fluorescent dyes and staining protocols for virtual hematoxylin and eosin imaging using ex vivo microscopy. We can ask ourselves why virtual pathology is important. One of the possible answers is in rapid diagnostics of positive surgical margins. In the US, positive surgical margins occur in a range of 4.32% up to 35% of surgical resection cases. The appearance of positive surgical margins leads to further oncology treatment or even to new surgeries, which will influence patient outcome and health cost. Currently, positive surgical margins are diagnosed using post-operative formalin-fixed paraffin-embedded histology. This procedure includes the following steps: tissue acquisition, sample validation, fixation and hardening, physical sectioning, staining and visualization, and final diagnosis. Time to fulfill all those steps range from several hours to several days, and is not suitable for any intraoperative diagnostics. On the other hand, virtual pathology can reduce the needed time by skipping steps of fixation and hardening, physical sectioning, and sample validation. Today, there are several imaging approaches that can produce virtual pathology image, such as structured illumination microscopy, light sheet microscopy, multiphoton microscopy, nonlinear microscopy, microscopy with ultraviolet surface excitation. Here, we will concentrate on analysis of the staining procedure and staining dye that are in use. I invite you to check our virtual pathology biopsies, clinical data, and rapid diagnostic system for virtual pathology of organ on the following talks. The majority of virtual pathology techniques rely on fluorescence effect. However, this presentation will not compare image formation techniques, but rather the staining procedures and staining dyes, because they are general and can be used with the majority of the systems. This table shows the most common cytoplasmic ECM and nuclear dyes. It's worth noticing that there is a large dye pool for nuclear dyes and that acridine orange can be used for both purposes. Also in the table, we listed major dye solvent and tracing solution that our group has used and that are also reported in the literature. One challenge for the field of ex vivo microscopy is that while the field has settled on a set of useful chemicals for staining tissue, the particular protocols used can have large effects on the quality of image obtained. Yet, a diverse set of staining protocols are reported across research groups and even within research groups. Our group is also guilty of this. While research papers may represent in depth which staining procedure is performed, rarely is there a rationale for why that procedure is used. Our goal in this work was to systematically and quantitatively study the variable parameters used across these different staining protocols, with the hope that we can better understand how to identify, design useful, repeatable staining protocols. In this work, we set up an experiment using eosin, DRAC5, and TOPRO3 as stains, as well as PPS ethanol, acid ethanol, and DI water as a rinsing solid solution. In this work, we also quantified the effects of dye concentration, staining time, and tissue condition, in particular tissue pH. In further studies, we will add more stains, primarily SPR gold, and look onto the effects of staining, order, and photobleaching. Assessment of the staining protocol, we used a standard image analysis routine. For the image acquisition, we used our open-top structure illumination microscope that performs optical sectioning. Our SIM system uses a spatial light modulator to illuminate a sample with predefined patterns. For this experiment, we use a 10x magnification objective and CMOS camera. To be able to produce a sample of the same size, we 3D printed a toolkit for slide and sample holder together with a sample cutter that is like a needle biopsy puncher, or cookie cutter that can cut squares of 2 by 2 centimeters. We also fabricated a sample compressor. We used the Apera Instrument LabSense 751 pH probe for solid materials. To keep the tissue samples relatively constant, we used bovine muscle and we performed cumulative staining for time-based studies. That means that for one solvent and rinsing solution pair, we imaged one tile of the sample and then provided additional stain to it between imaging sessions. Between two exposures to the stain, we did not refill or change the staining solution to mimic continuously staining. For the cytoplasmic ECM dye, we used Eosi. We either diluted Eosi with ethanol, acid ethanol, PBS, or DI water, or used the stock solution undiluted. For the rinsing, we used the same chemicals as for Eosi dilution. Here is the concentration that we used in micromolars. The highest one represents stock solution, and the lowest concentration represents 1 unit of Eosi and 500 units of any solvents. We did 5 time points imaging after a short dip, 10, 30 seconds, 1, and 3 minutes. Concentration and imaging point for Eosi and other stains are chosen to be around our current image protocol. Also, they reflect our interest in intraoperative visual pathology, so longer time staining with lower concentration was not something that we investigated. For nuclear dyes, DRAC5 and TOPRO3, we used the same procedure with dilution only in PBS, which was the dye manufacturer suggested, and ethanol, and for rinsing we used all solution except for the acid alcohol. Here we did 4 imaging points after a sample is staining. For the 30 seconds, 3 minutes, 5 minutes, and 10 minutes. The only difference was the concentration that we used. 10 and 50 micromolars are used for both TOPRO and DRAC5 with both solvents. With TOPRO3, we included one more dye concentration of 4 micromolars, and for DRAC5 PBS solution, we used an additional 1 micromolar and 75 micromolar. We did not check other solutions for DRAC5 since ethanol was not recommended as a solvent and due to DRAC5 high cost. Together with imaging, we performed 3 pH measurements for each imaging point. pH values was measured on both sides of a tissue, on the stained surface and on fresh tissue surface, and we also measured the pH of the stained solution before every restaining of a sample. As I already mentioned, we use optical sectioning SIM for image acquisition. We acquired 3 patterns images with a pattern phase shift of 60 degrees that will allow us to perform square law detection to remove any unfocused light. Image acquisition and processing are performed by using custom-built LabVIEW and MATLAB software. For sample illumination, we use a 528 nanometer laser for Eosi excitation and a 640 nanometer laser for nuclear dye excitation. The power of the laser was manually optimized to provide the best images. Images are captured by 248 by 248 CMOS camera with a 25 millisecond exposure time. For imaging the whole sample tile, we needed 16 by 16 frames acquired that are post-processing stitched using ImageA. From the sample image, we choose 5 regions of interest in which we will extract quantitative parameters. ROIs were 5 by 5 millimeters for cytoplasm, ECM dye, and 1 by 1 millimeter for nuclear dyes. Our statistical analysis is based on the calculation signal-to-noise ratio for nuclear dyes and image contrast for cytoplasmic ECM dye. We choose these 2 measurements due to the properties of acquired images. Nuclear dye fluorescence images provide sparse images that preferably labels the only nucleus with no background information. On the other side, cytoplasmic ECM dye labels much more structures in the tissue and contrast as a measurement of several distinct features on the image is more suitable. Finally, we used our pH measurement to correlate tissue pH change with a change in image quality. This measurement can be interesting because tissue pH can vary depending on the tissue type or how fresh the tissue is, and is not a parameter that has been studied before to our knowledge. Previously, we were using 7 different Eosi concentration and image each concentration 5 times. Also, we dilute Eosi in 4 different solvents and use 4 different rinsing solutions. That creates 380 data points, which will be overwhelmingly to display all of them for this short time. So we will point just the most important trends. First, we will compare contrast dependence on dye concentration and staining time. This is a reasonable comparison because results for the same concentration much more depend on staining time than to solvent and rinsing solution. All data of the same concentration and staining time are averaged and showed without error bars for clear visualization. We observed that for higher concentration, lower staining imaging time is needed for high concentration contrast value. And for the lower concentration, we need longer staining. We think that first occurs due to overstaining and later due to understaining of the sample. Also, here we can see that all concentration achieves similar peak contrast value, except the 2 smallest concentration that still has an increasing trend. To emphasize this behavior, we plotted peak contrast image segment for each concentration. The largest 3 concentration peaks after 10 seconds of staining time, middle value concentration peaks after 30 seconds, and low level concentration provide maximal contrast after 120 seconds. When we have a general contrast trend with time, we can analyze how different solvents influence contrast. For that purpose, we fix concentration on 5,400 micromolars, which is one of the middle concentration that we used, and plot contrast dependence on staining time and solvent used. From this figure, we see that for given concentration, spread of contrast values depends more on staining time than on solvent, which supports our previous claim for averaging data over concentration. Also, we can see that ETOH solvent follows the contrast pattern of average data. We observe the fast decline in contrast when we diluted Eosi with acid ethanol. We think that this happens either to the rapidly changed pH value of the dye caused by mixing with the sample or due to the mechanism of dissolving Eosi in acid ethanol. Finally, PBS and DI solvents do not present any noticeable feature except that peak contrast values are overall lower than for ETOH, indicating that ethanol is a preferred solvent for best contrast using Eosi. For further emphasis on the rapid drop of contrast when we use acid ethanol, we show the image segment with the highest and lowest contrast for ethanol, where we can see some blurring on the area with oversaturated Eosi signal due to a long staining time. When we show the highest and lowest contrast for acid ethanol on this concentration, we can see that on highest contrast we can see fine structure and details in the muscle fiber, comparing to low contrast image where the signal is still high but no details in the muscle fibers are visible, indicating that the best contrast with the acid ethanol is achieved with staining times as short as a quick dip. Finally, we can compare the effects of the rinsing solution on contrast. For this purpose, we will show here contrast dependence on staining time and rinsing solution using a stock concentration of Eosi. This will help us to separate rinsing influence from solvent influence. We can see here again that staining time is a much bigger factor than the rinsing solution. Ethanol rinsing showed the fastest sample drying time and higher contrast overall staining point. We observed interesting behavior on acid ethanol that can explain rapid contrast drop, as we were unable to see any dye removal in acid ethanol dish comparing to ethanol dish after 5th imaging point. Finally, PBS and DI water show similar rinsing efficiency. However, their contrast was also rapidly dropping due to slow drying and large droplets of liquid that still exist on the tissue when placed on the slide. We will analyze drag 5 and topper 3 in a similar way. For drag 5, we use 4 concentration with PBS solvent and 2 concentration with ETOH. We acquire 4 images for every dye concentration and use 3 rinsing solution. Here, we did not use acid ethanol. For all concentration except for 1 micromolar, best SNR is obtained with staining time between 3 and 5 minutes. For the lowest concentration in our range, peak SNR happens after 10 minutes of staining and trend is still increasing. For the higher concentration, SNR drops at 10 minutes imaging time and tends to further drop. We show image segments on the peak SNR for each concentration. With drag 5, we check only one solvent other than PBS and did not observe significant difference, except the trend that PBS diluted drag 5 had a larger SNR than ETOH in each point, which we can see on sample images too. For the rinsing solution, we did not observe any important difference. PBS and DI water gives very similar effect. For topper 3 imaging, we use 3 dye concentration, 4 staining times, 2 solvents and 3 rinsing solution. We can see that for this dye, also optimal staining time is between 3 and 5 minutes. Also, we observe higher SNR in shorter staining times with topper 3 than with drag 5. Image segments show peak SNR for each concentration. Solvent solution did not produce any significant effects and had a comparable SNR. On the other side, rinsing solution made significant difference between PBS and the other 2 solvents. To emphasize this difference, we show small image region which is rinsed with PBS and ethanol. And we can see more background on ethanol rinsing comparing to PBS. These images are from largest difference that occurred on 15 macromolar topper 3 concentration. Finally, we can compare drag 5 and topper 3. Their peak SNR are similar. They are reached for both cases in similar staining time and dye concentration. One of the main differences is that drag 5 is more specific dye for nucleic acids than topper 3, and because of that we can see increased background on topper 3 images and as in ethanol rinsed topper 3 images. We also note that topper 3 can be taken up by non-biological materials such as tissue fibers or other contaminants, resulting in very bright artificial such as shown here. In conclusion, we analyzed 3 fluorescence dye, Eosi, drag 5 and topper 3, that are commonly used in virtual pathology. We found that for fast staining, optimal range of concentration for Eosi is between 1200 and 5400 micromolars, with staining time between 10 and 40 seconds. For drag 5 and topper 3, any concentration below 10 micromolars will require staining time longer than 180 seconds. We found that solvent and rinsing solution had no greatest effects on contrast for Eosi staining, although moderate, and did not play a huge role to image quality for nuclear stains. Exception: acid ethanol for Eosi, which can be connected to a large drop in pH of stain and tissue, and ethanol for topper 3, which results in higher background. We will look forward to using this data to narrow parameters range in future protocols and to better understand tissue pH influence on image quality. In the end, I would like to thank you for your patience and to thank to my colleagues at Tulane University Translational Biophotonics Lab and to our funding sources.